like in just a couple of minutes. There is one small thing that I just want to say. So for those of you who got their tickets for the concert tonight, you didn't get a confirmation. That's normal because we used a Google form, and if we wanted you to get a confirmation, you would have had to have a Google account. And I knew it was going to be a problem for some of you, so that's why you didn't get the confirmation. So as long as you filled out the form, you will be on the guest list. There is no tickets or things like this. Tickets are for normal people. You are special this evening. And because you are special, you are basically just on the guest list. So when you get to the concert venue, you just tell them, oh, I'm on the guest list as part of Linux Audio Conference. Then they will check that your name is on the list, and then you'll be able to get in. You know, like that's how it's going to work. If you didn't get a ticket, yeah. Les sacs à dos dans le. Yeah, I think it should be okay. Yeah, like, yeah. Sorry, this is not a very affirmative answer, but yeah, it should. I mean, it's not like a club, you know. Like, it's like half club, half restaurant, half, you know. Like, so I think it's fine, you know. Like, they should be okay. If you didn't get a ticket, it's probably too late now to be on the guest list, but you can still go there and pay for your ticket, you know, which is only €8, you know, like so. So it's not that much money anyway. But yeah. Any questions? No. So to get there, you can take the tram here. You take T1, not T4. T1. All the way down to the end of the line to Musée des Confluences. It's like 45 minutes of tram, basically, and that will take you there. Yeah, no changes, no, it's all direct. So, yeah. Anyway, I'll hand in the mic to Frank, who's going to chair the next session.
And adding to that about getting there, Herman told me this morning that it might be faster to take the metro instead, which would be going much faster than the T1.
Yeah, the metro is another. Well, the metro doesn't go all the way to. Yeah, then you walk. Then it's a lot of walking. Like the metro will be. It will be probably faster to take the metro, but then you'll have to walk for like a solid 15 minutes under the sun. So. There is air conditioning in the tram, so, you know, like, might be actually easier to just take the tram. You can eat at Le Sucre. There's, I mean, it's a club, you know, like, so the food is not great, you know, like, it's more like, you know, like charcuterie, cheese, or whatever, you know, like, it's more like a bar kind of stuff. There is not a lot of restaurants in the area there. It's like an industrial area, you know, like so. So if you want to get like real food before going there, you should probably stop somewhere in between, you know, like. But there is not a lot of options. But again, they'll have like burgers, hot dogs, or you know, like basic stuff. Yeah.
And perhaps get your bath trunks in case you want to jump into the sauna for a quick bath. All right, then welcome back. I'm Frank. I'm your timekeeper demon for the next 3 talks. So our first one is then Thomas Meyer from Germany. I don't even know from where in Germany you are.
I'm from Munich.
From Munich, okay, yeah. With this presentation on using Android smartphones to control music software with open sound control, using sensors to OSC. Thomas, stage is yours.
Yeah. So thank you for the introduction, and thank you, Romain, for organizing this conference here. Basically, what I'll do is give an overview over the app sensors to OSC. I'll give us a few demos and practical tips. Basically, Sensors to OSC is a flawless Android app. It's, you set up your sensor data that are available on your phone, and you send them via OSC to any receiver. And I've developed it in 2014, and for the last 10 years it's been pretty much stable, and I have only included some new features on newer Android versions, but there's not much that I've did about it, and it was working, and I think it's a nice prototyping tool when you're thinking about using sensors that you want to use, and so I think I wanted to share it with you. So the basic idea was in around 2010, a lot of people were working with Wiimote and Kinect, and you had to buy a device. And smartphones are basically obsolete after a few years because they don't get any security updates, although many people are not that much concerned about security updates, because when you look around how many when you walk around with some Samsung smartphones, you can connect to any TVs that are around and send them your photos. And smartphones have many sensors included, and communication via Wi-Fi is ubiquitous. So I've wanted to reduce e-waste that we've heard yesterday also about the old smartphones that we don't want to use. So the design decision was it should be easy to set up, should support basically everything that is available. It works from Android version 4.0. I even have a build available that on my website that is working with Android 2.3. If you have some old device, because someone 2 years ago asked me about it, and I then replicated it, and I did manage to get a build. And it should be as generic as possible. It should expose all possible sensors. And I only use UDP because any self-respecting programming software that can interpret OSC can use UDP. So this should be enough. And the data interpretation should be on the receiver side. And here's some feedback that I've got, especially someone got it to run on watchOS, and I've got a bug report because the portion at the top is staying and cluttering the screen, so I've made a different layout for clocks for watchOS. So I mainly get feedback because something is not working, and then I implement it, and then I let it go. And different phones expose different kinds of sensors. Here is the list of sensors on my Fairphone 3 with Lineage, and it's a lot of sensors, and stock Moto E3 does only expose 4 sensors, so basically that's what you're left with. And I'll show you some short demos. And just a second. Basically. Yes. This is I'll have to restart screen copy. So, yes. So I've set up the IP address and the port, and so basically I'm already sending data here, And I've selected accelerometer and orientation. And I've set it up so that I use, for this example, I'm using the orientation. That is, just a three-value floats array. And I'll use the touch for controlling synapse sub-effects. So basically, I use the tilt of the phone to control panning. It's the roll, excuse me. I always get it wrong. And this is the pitch, as it's called. It's controlling the filter cutoff. And the third one is the azimuth, which is controlling the filter Q. And then I use multi-touch to trigger nodes. So. So that is a simple example. Another one is you could, which I use quite often, is you can mount your phone on your, for example, on my guitar, and then wire it through the computer. This I will emulate it by playing a sample. And then using the accelerometer to pan the signal or pitch shift it. So I'll just. So just think about your guitar. So. Yeah, so that's what I'm using most of the time, but of course you can use other sensors, for example, the proximity sensor. You see it's 0 or 5, which can be used for triggering something. It's the first value that is changing, and of course there's the light sensor. I'll get into detail about it later, and my latest addition is the Bluetooth sensors that I've activated here. And here is a cycling crank sensor that whenever it gets updated, the value should update here and should count up on the first value. So maybe the Bluetooth connection is closed. So basically, that's what the app is about. And yeah, so I'll just move screen copy away. So some practical tips about the sensors. Accelerometer is a 3D vector with the value in Newton in each direction, along each axis. So changes are not independent, basically. When you move your phone in this, when you tilt it in this way, then acceleration in this direction changes as well as in this direction. So there's the orientation sensor as well, which is in 3 different directions. The azimuth, which is basically the rotation to the north, the pitch, and the roll. They are independent, but at the end you get discontinuities. So you will need some way to compensate for that. Light sensor is a bit tricky to use because We have all seen it when we are using our phones outside, and when we are a bit in the shade, the phone is too dark. That's the sensor that is triggering that. And the proximity sensor is, should in theory output the difference in the proximity in centimeters, but basically it's just 0 or 5. It's the sensor that deactivates that you are dialing with your ear while phoning. So, and the touch that I've shown is there's 2D Cartesian coordinates from 0 to 1, and the lifted finger sends -1 for both, so you can compensate for that. To reduce network latency, you should use a dedicated Wi-Fi router, not as I do today with another smartphone here. And you can set the data rate to read the sensors, and there are three settings. So one is the screen rate that is only triggered when something is happening on the screen. Then there's the game speed that should be used for games, and that is okay-ish, and for most applications should be okay. But there's also the so-called fastest setting, and yeah, the Android documentation doesn't specify what it means, but basically it should mean every time there's a change. So, and of course you should only send the data that you need, and when you use multiple devices, just use different ports. As we see in this picture here, that was for a performance that we've had in Munich. So we had dancers equipped with smartphones on their body, and they were controlling the sound with their movement. In addition to musical performers that were jamming to this sound. Unfortunately, I don't have any footage of it because the camera died while recording this evening. So that was the feature set that I've had 10 years ago, and that I've had in November. And then someone emailed me if I could integrate Bluetooth sensors. So I consider this experimental, not because it's not work, because I'm not sure if the data transport is done good enough to meet up to make it easy for users. So basically, currently, only the sports-related sensors are implemented because it was easy to copy the code. And basically, and you get the OSC address, which starts with BT for Bluetooth, and then the sensor name, because there's already a heart rate sensor, for example, declared in the Android sensor list, and there's devices out there that are that have an integrated heart rate sensor, so I don't want to clash it. And it will not work for so-called companion devices, which are devices that don't show up in your Bluetooth connections, but are only working with a specified app. So these cheap I've tested one of those cheap wristbands because I've got one from a relative who can't use it anymore, and there's no way to get to the data. So my open questions are mostly about the user experience that I want to provide, because there's 261 sensor types listed in the Bluetooth specification, and basically what you get is you get a UUID of the sensor, a UUID of the sensor of the device, excuse me, a UUID of the sensor. sensor type, and then you get a byte array, and that byte array has to be interpreted according to the specs. And doing that for all 261 is a bit much work for something that nobody is using, as far as I know. And so, should I say? So I'll just get back to screen copy and show you my main concerns with it, because when I look at when you look at for example here at the accelerometer, you see the OSC address it is sending the data to. It's just /accelerometer. When you go to the help, it lists all available device sensors, and for the accelerometer, it says it sends 3 values, and the max range that this device supports is 78 newtons. So everything you need for documentation is on the device, but how can I handle it for Bluetooth? I don't know. That's an open question for me, and that is something that I haven't figured out yet how I should do it, and so that's why I've called it experimental, because I haven't fixed the data that I'm sending out, because I want to have. I don't want users to have a negative experience when they update their app, basically. So, especially how should I handle the same thing if I have multiple Bluetooth devices connected to the phone and they have the same gut profile? Should I include somehow the UUID of the device, which is also quite hard to discover for an end user? So that's a bit sketchy territory for now. So, yeah. Another one, just a small app that I've made, is because it's a byproduct of Sensors to OSC. It's an app called Alligator Bytes. It is I have made it as the performance app for the Alligator Gozaimasu collective, which was formed in 2015 by 2 artists from Munich that were on an artist exchange with Sapporo, because Munich and Sapporo are sister cities, and because they both hosted the Olympics in '72, and then the artists and then Sapporo artists came to visit to Munich, and it's basically a sample looper with pitch shifting, speed change, panning, and you are able to break up samples. It's implemented using libpd and orientation sensors. I won't demonstrate it right now because if you're interested, we can talk about it. I can show you later. Thanks for reviving the heavy compiler, because I think I'll give it a try to optimize the code, because well, about the Alligator Gozaimasu collective in 2020 something happened, as we all know. COVID started, and so we were doing some we were exchanging sound files online via a Nextcloud instance, and so a lot of people invited others, and so it went very global. And we have people from Indonesia, Ukraine, Scotland, Amsterdam, Brazil, etc., all in the collective that are contributing. And we've had there were 2 festivals in Munich with that collective. But of course, it's always a problem, especially for developing countries like Indonesia, to get modern smartphones. And so we try to use it to make the app as performant on as possible, even on older smartphones. And so, yeah, I will use Heavy to make it more performant. So what we want, what is currently capable of is you can load and export samples or even whole sample packs, which are just zip files with samples and JSON configuration. You can record the sessions. We have to do some optimization for the UX and the help somehow. And we want to release that on the Play Store. And because of some Google rules, you need to have a lot of testers. And we are basically yeah, the cool people I know are using Android without Google, and the not so cool people are using Apple. So, the wannabe cool people. So yeah, we need some testers for that, and yeah, since we're here a lot of people that are speaking German, I've included this slide. And yeah, and basically that's it. You can get both apps on the F-Droid, and code is available on Codeberg. And below you see my contact data. Thank you.
Thank you very much, Thomas. Are there any questions? Okay. And while I walk up there, I asked my own first question. I was just wondering, the proximity sensor you said is digital, only 0 or 5. Is that true for all the phones, also for the Moto? Are they all just digital?
All that I've tested. I haven't tested all phones, but all that I have had in my hand, we can try that.
Okay.
Have you considered normalizing the values from 0 to 1 that you send from the phone, instead of sending the raw range?
Yeah, I've considered it, but it's a bit tricky, especially when you think about the accelerometer. You query the sensor for the sensor range, and it gives you one value for each for each axis, and so basically, and for the orientation, it's it would give you 2 pi, and then. You would have.
Well, the more general use case would be to get rid of the middleware, like so you can set your own path for the OSC, and you can send it directly to Otter, for example, or to any other software that already understands OSC, without having a middleware to first translate or unpack the values.
Yeah, I've considered that as well. Okay. Already, and it's yeah, it makes it harder to set up, because then you have to, for example, you would have to you would have to set up the range for for example, when you want to use the accelerometer, you would have to set up the range for each axis, and you would have possibly want to send one axis to one receiver and the second axis to the second one, and then to edit it on the phone. While it's harder, yeah. I was considering it, but I've decided against it because I think it's, in my opinion, it's easier to have some middleware, because, yeah.
Related to that, but from a musician's point of view, have you considered sending MIDI instead of OSC? Because then you've got a large number of ready-made defined functions that will be broadly available on almost any musical instrument?
I have thought about it as well, and yeah. I think that that's a good idea to have it in a separate app, and then you have to define what sensors you want to use for what, because not every phone and every device supports all sensors, as we see here. The stock Moto E3 doesn't even support an orientation sensor, which was the case for all Moto E models from 1 to, I think, generation 4. And so if you want to use the orientation sensor for something, and you have to do some mapping and you have to have a fallback for devices that don't support the sensors that you want to use.
So I would second what Robin said, but I understand. I mean, it's a decision to not have any kind of like local mapping. What I would want to suggest is, have you considered looking at the derivative of sensors? And I think that makes, let me explain. I mean, it's the same argument. You could do that somewhere else, but you could reduce the data rate. So for example, I was playing with the app while you were giving the lecture, so it's great. Thank you very much. Of course, it keeps sending stuff at a fixed rate. And it would also be interesting to be able to limit that. So for example, I'm looking at the accelerometer, my phone sits here, and it would, the tiny jitter that it always has, we would kind of gate that, and then do the derivative of the values. So only relative motion is sent ever, and only if it really moves. Because for some applications, having so much data flow, if for example you were showing dancers, like I'm picturing having 10 dancers on the same access point, it could get kind of busy. So in order to like clean out data locally, and that would be an argument to actually do it in the app, even if you said, okay, it would be middleware can do the data shaping, let's say, but reducing data rate. That's my question.
Yeah, I've looked into it, and if there is no jitter in it, it will only send the data on change. But of course, there's a small jitter in it. At least for when you use, for example, the proximity sensor, or the light sensor is a bad example, because it's always some value that are changing because of some shades or anything. But yeah, it will only send on change, but because of the small jitter, and it's hard to say what is the threshold. But when
Slider. Just give it a threshold.
Yeah.
Just give it a threshold slider.
Okay, yeah, that would be an option that I will consider. Yeah.
So speaking of limiting, I wonder if you ever ran into any issues with bandwidth in a more complex setup, such as, for example, the one you played live on Wednesday, and having multiple accelerometers. All sending data at the same time. Do you ever run into any delays with buffering, for example, of UDP messages?
I've not come to, well, when I'm using a dedicated Wi-Fi router, like this, even this cheap one, that's fast enough with, at least for my performance, with 4 smartphones, and it's not buffering the UDP data.
Okay, I think we have to stop here. The time's up, and I don't want to be the first one to kill Romain's timetable. So thank you again, Thomas. Setting up the next speaker, Bill Ferguson. Don't fall asleep now. Okay, then our next speaker is Bill Ferguson, coming from the Virginia, right? All from the University of Virginia?
No, Virginia Tech.
Virginia Tech, sorry, okay, close to it. Four writers, you are one of them, including also Itzo Bukvic, Justin Kerobo, and Bradley Davis, talking about bringing WebPD to LAC, bringing the Linux Laptop Orchestra to the browser. Go ahead.
Yes, thank you. So as you said, we have been working to bring PDLork into the browser. So I know all of you are familiar with Pure Data, but for those of you who don't know what PDLork is, it is a fork of Pure Data, as we were talking about all the forks earlier. So it was forked off of PD Extended, and then broke off into Pure Data, and then we came back off of Pure Data, and then now we're back into PDLork. And then now we have WebPDLork, which is a web runtime for PDLork. So the Pure Data forks are continually expanding. As for why we wanted to run it in the web, we have been using PDLork for education in like K-12 schools. And a lot of times their IT infrastructure isn't able to have the resources to install different software on all of the computers. So everyone has a browser, so if we're able to upload patches and have them be viewable in a browser, it's much easier to use them for education and then introduce kids to this technology. So there was some prior work in this area in, I believe it was 2020 or 2021, by Zach Lee. For the Google Summer of Code, he made something called PD Web Party, which he used Emscripten together with libpd to run Pure Data patches inside the browser. And I'm like, surely that's not mine. And it supported some subset of externals and patches, but there were a lot of limitations that then we sought to address. So there was no support for abstractions, so all the patches had to be, all of the patch had to be within its one file. Wired connections would not work. If you had GUI objects and they were connected to something using wires like this, it would just not work, nothing would happen. There's no file I/O, there's no networking, no graph on parent, and only a small subset of GUI objects were even supported. So you could have only like toggle and bang and a few other things. You couldn't even have messages to click like to start or stop any of your patches. And also only had a limited amount of externals, which I know for some people that doesn't matter as much, but for others, that can be really important, especially if you're using Cyclone or something similar. So we began to address these limitations. We added patch preprocessing to preload the abstractions so that then you could use abstractions in the patch and it would fetch them from wherever the original patch came from and then put them in. And then we also made it so they could handle graph on parent. They was able to do that now and handle more GUI objects. We added support for all of the GUI objects that you're familiar with. And we also added this lovely thing that you can see that looks like a bunch of gibberish to convert all of the wired connections to wireless connections so that they can work inside the web environment. So none of this would be displayed. The web environment only displays as if it was a graph on parent, so you only see the GUI. You don't see the connections. You don't see any of the mess. But now everything works as you would expect. We also added some runtime support for file I/O. So when it's running in a browser, it has a virtual file system, but obviously it's not a real file system because the browsers are all sandboxed. So we added a kind of middleware in between, where when it tries to read a file, if the file isn't in the virtual file system, it'll go and find that file. So if the patch was hosted on like some website, it'll go to that website where the patch was and see if the file is right there next to the patch and load it transparently to the patch, so the patch doesn't even know. And then similarly with networking, if a patch tries to use networking or connect out to a server, networking does not exist in the same manner in the browser as it does on desktop. So we added a middleware which will intercept the network traffic and then convert it into WebSockets, which is what browsers are able to use. And then that will then get relayed on to wherever the patch was actually trying to connect to. So we have the PD internals, which will interact with I should have had this while I was talking about it, but it'll interact with the virtual file system, which if it's not there, it'll reach out to the web PDLork, which will then reach out to wherever the patch came from and find the file that's there. And then it's a similar story for networking. Next, we added more externals. So things like Cyclone, things like PDLua, that wherever Tim is, that you were talking about yesterday. Unfortunately, we're not quite up to date with the graphics, but we'll get there. PDJS, Flight, and all the other externals that were supported by PD Extended and are supported in PDLork. So now all of them work inside the browser. We have support for multiple windows. Similar, like if you want to open a subpatch, you can do that, and they'll show up as little pop-up windows that are in the same context as the main window, so they can interact with the patch as you would expect in a desktop version of Pure Data. Now for a little quick demo, I have one patch right here. If anyone wants to open it, I will also open it. This is just a simple equalizer, but just to demonstrate the basics. Where's my mouse? Oh. Do I have any? Yeah. So just a graphic equalizer, exactly what you'd expect. And it works fine. Oh, turn it off. And then the second patch here is the patch that we've been kind of using to benchmark WebPDLork's functionality. This was designed by Dr. Bukvik. He has been using it for musical performances. It's called Lork Tweeter, which I also have open here. And so you can see this is quite a large patch, and it works with very, very similar performance inside the browser as it does on the desktop, and it's a full synthesizer. So you can do pretty much anything in WebPDLork that can be done in the desktop version, including we have a server for multiple users to all perform at the same time. So even that can be connected to from the browser. And it looks like someone's in there, so I'll let them be. So there are still a few limitations of WebPDLork. What I was mentioning with the opening in sub-windows, for whatever reason that we have not figured out yet, if you close those and then try and open them again, it does not work. So that's an interesting limitation. And then, of course, with it being in a browser, you don't have the same kind of control over what audio API is being used or exactly how the devices are set up. But that's sort of an inherent limitation. And then persistent storage, if your patch wants to save something, currently that just gets saved in the virtual file system and there's no way to get that out. So as soon as you refresh or close it or do anything, that is gone. There's also no editing. We focus this so far on the workflow of you create your patch, create your work on the desktop, Pure Data, and then you upload it, and it's an easy way to share with other people so that then they can use it from wherever without having to have Pure Data installed. But there's currently no editing. And we also have no central repository for the packages. They have to be hosted somewhere. Although we do run WebPDLork itself, the runtime, we only have a certain set of patches up there, and to open your own patches, you'd have to have them at some web accessible location or host your own version of WebPDLork. So with that, that's all I have to say. So any questions?
Yeah, so we do have questions, of course, in the last rows. I think, Albert, maybe you were 2 seconds early.
Thank you, Bill. How does the server setup look like? Is that a full PD-log system, or are there some restrictions?
I'm sorry, you said a full what?
The server setup, the server side, which serves the PD-log program to the browser.
So we have a Docker image available in our GitHub, which I think I might have forgot to put the link in here. But we have a Docker image, which it can be run through that, or it can be compiled from source. All of the sources in our GitHub. Once the runtime is compiled, it's just serving static files, so it could be served through any sort of web server.
Okay, thanks.
I wonder, when a Pure Data patch is running in the browser, can you use the OSC receiving objects because they would attempt to create a UDP socket, and I don't think that the browser environment would allow that, or would it? Does it support OSC, or have you not looked into that? Thank you.
I have not specifically tested OSC. I don't personally have any OSC devices to test with. I do not think, as you said, I do not think UDP would work right now. TCP, there's full support. I'm not familiar enough with OSC to say if OSC could also use that. If it could, then it might work. But currently, there's no UDP, and that's something that we can look into.
Hi. I know that PDLork normally uses JavaScript to render everything in the window. So how much of that is reused for the web version, or is the whole UI here basically all new and from scratch?
The whole UI is pretty much separate because there's some different considerations that needed to be done in order to make it run in the browser. So rather than having a whole bunch of different cases, we just the web UI is separate.
That makes sense. So then a small follow-up is, how's the compatibility between the GUIs? Like, for example, I think you include Cyclone as well. So Cyclone also has some user interface objects and stuff. Is that all completely supported?
Right now we have supported everything in WebPDLork that we support in regular PDLork. And as we've been supporting more things, we add them to both at the same time.
Fantastic. Very impressive.
Any other questions? I just realized now, this year we don't have any IRC questions, right? We used to have that, and people watching the stream would ask questions, but we don't have this time. Okay. Well, if there are no more questions, then thanks again, Bill. And we need 2 minutes for the next speaker.
Do you have a mouse? Yeah, but I needed to. I don't have one. There's a touchpad. You need a mouse? I have a mouse with me. It's a... You need one? Yeah, sure. You can get one. Yeah, I'm sorry. Use touchpad, it changes the pages. Oh, yeah.
It's working. Yeah, I don't know if you're left-handed or right. Yeah, and when you need me here, you call me. Yeah.
We can start if this. Okay, this is nice.
Yeah, this is embarrassing in Linux Audio Conference, starting a talk 14 minutes early. Wow. For those who were not there in 2003, I think in the end of the first day we had about 1.5 hours lag, so different story. Okay, our next talk in this slot needs no introduction, I guess. When there's LAC, Fons delivers, and he did this countless times. And again, he submitted a second paper this year, which is about his tool ATL1, which is kind of, if you know Auto Talent or Auto Tune from Antares from back in good old Chair 90s times. It can do that kind of thing. It worked for me once to improve my own singing. It made it a little less awful, but I think there's a new version now that you want to present, Fons, so yep. Go ahead.
So the auto tuning has become more or less a standard effect used in lots of music today, and can be used as an effect, which honestly I dislike, or you can just use it to correct small pitch shaders for singers who cannot sing exactly in tune. So it's certainly a matter of controversy, and some people hate it, and that includes me. So why did I do this? Because it's an interesting project. So I wrote Zeta 81, Autotune 1, I think 10 years ago or something. And then it was turned into an LV2 plugin by Robin, and which made it a lot more usable, because then you can automate the controls, for example. There's a YouTube video of someone using it in another session with the controls automated. It was quite convincing. And the only problem this YouTuber said is that the plugin, the 81, does not preserve the formants in singing voice. And that's true, that is a big problem. So this one, second version, second release, will fix that problem actually. Yep. So why didn't Zeta 81 preserve formants? Because it used resampling to change the pitch. And we fixed that, and we use that by using a different algorithm, which I will speak of later. So at the moment, this is a jack application. It's still being developed and improved, but Just as with the tape sim, the usual suspects will turn this into an LV2. So, what is the problem? Singing or speaking human voice can be of two types. It can be voiced or unvoiced. Voiced means it has a pitch. So you have the vocal cords which vibrate at a certain frequency, and that signal is then filtered by the rest of the path up to your mouth. So the pitch is the fundamental frequency of that waveform. It's usually very rich in harmonics, so the filtering will create peaks in the spectrum at certain frequencies. And these are called formants. So when you retune, you want to change the pitch, but you don't want to change the frequency of the formants. Then an unvoiced signal is one that is made without vibrating vocal cords. It's just noise which is filtered. Yep. So, as I already said, we need to change the pitch but preserve the formants. And unvoiced parts are not modified at all, okay. There are three steps. We need to find the pitch that is actually present in the signal, the original one. We need to compute the correction. Oops. And we need to generate the pitch shifted signal. So the first step is more or less the same as in the previous release. It just has been improved a bit. The second and third steps, they are very new. They are completely redeveloped from scratch. So the first step, pitch detection. We need to detect if a signal is voiced or unvoiced. And if it is voiced, we need to find the fundamental frequency. There are many methods for that. There are lots of papers about this. The way, or the algorithm used by 82 and 81 as well is autocorrelation. It's a mathematical calculation, and it finds out how similar a waveform is to a time-shifted version of itself. So if you find a similarity at a certain time shift, then there's a good chance that that time shift that corresponds to the period of the waveform. So the efficient way to compute it is as the inverse FFT of the power spectrum. It works well in practice. There are some corner cases, there are some difficult cases, but in general it works very well. And in Zeta 2 this is done every 5 milliseconds, which is more than necessary, but that allows to add some sanity checks. So how does it work? You take your signal, fragment should be at least 2 pitch periods long. So for the male singer, the lowest pitch which should normally occur is something like 80 Hertz, which is 12.5 milliseconds period, so we need at least 25 milliseconds of signal. Then you do some band passing to remove the parts that won't help. Apply a window, do the forward FFT and compute the power spectrum. FFT must be longer than the window to avoid cyclic effects. That's a general problem with FFT-based things. If you have an endpoint FFT, and you have a shift in your signal of X samples, then for the FFT, that is the same thing as having n minus X samples, so you cannot separate the two. So if you have this effect, which will occur for very low frequencies, then autocorrelation will give the wrong results. And the way to avoid that is to make the window shorter than the FFT, actually. Then you do the inverse FFT, and you find the autocorrelation. You can normalize this by dividing by the first sample of the output, which is just the signal power. And for unvoiced signals, the autocorrelation will be very small, even for very small delays, so they are easy to separate. And then you just select the largest peak in some allowed range, and you interpolate to find the exact position of that peak. Finally, add some sanity checks. For example, the current algorithm will, if there is any doubt, prefer the previous result instead of updating it. So here is an example. Here, the blue curve here is the actual waveform, 2048 samples of it. And the green line here is the window which I apply, which is a bit shorter than the FFT. Then to the right here, the green curve is the spectrum. So here we have a signal which has a fundamental frequency of 120 Hz. This is this very small peak. And some strong harmonics at 360 and 480. And the curve below is the inverse FFT of the green one, actually, which is the autocorrelation. So this will have a very strong peak at 400 samples, which with the sample rate of 48K means 120 Hz. So we have detected this frequency, even if the harmonics are much stronger. And that's one nice feature of autocorrelation, that it can do that. Oops. So if you do this on a longer signal, here we have 20 seconds or 10 seconds of a musical track. On top you see the level. And below we have the autocorrelation but plotted in color. Oops. Blue is negative, red is positive. So the largest peak here is where the green dots are. I use this tool to verify that the algorithm is working quite well. Oops. So here we have a corner case. We have a very weak fundamental, the same signal as in the other example, but with only a single harmonic, which is 30 dB stronger. So now the correct peak is actually this one at 400, still the same frequency, but the others are much higher. So this is only 1% higher than the previous ones. But still you get the correct results. Actually, in practice, this is not such a big problem because a spectrum like this in a voice waveform will not occur easily. Normally you had something like this, much more harmonics. So even just adding this fourth harmonic here reduces the peaks which we don't want, the wrong ones. So far for the pitch detection. Then we have to select the correct pitch. And in 82 there are two buttons controlling this. You can have auto mode and MIDI or a combination of both. So if both are off, then there is no auto-tuning. But you can still modify the pitch by a constant ratio, and you can also shift the form and the frequency. And the MIDI input is just ignored. So in auto mode, you can enable a set of notes in this small virtual keyboard. You can also select one key, for example. I will use it in the demo. You can select, for example, a major scale of G, and then it will just enable these notes which are in that scale. And then the algorithm will pick the nearest one of these notes. Doesn't matter in which octave they are, it will always take the nearest one. And auto plus MIDI enabled, that's the same thing, but if you have any external MIDI input, that takes precedence over whatever you have selected on the virtual keyboard. And lastly, we have the pure MIDI mode, and this is new. We didn't have that in 81. And then the last MIDI note which you played and which is still active will be the retuned pitch. Whatever it is, even if it is 2 octaves lower or higher than the real pitch, it will always use the exact absolute pitch which you are playing. And it will also include any shift pitch bend input. So there are some controls which are controlling this process. Range. You have 2 ranges of pitches which you can allow. The low range is for male singers, goes down to 80 hertz. The high range is only for female singers. And the only reason to use this is that it will reduce latency a bit. If you say, okay, the very lowest frequencies are not expected, then the algorithm can be preset to have lowered latency. Also new thresholds, anything below a set level is considered unvoiced and will not be processed. Can be useful in some cases. Then you can set the absolute tuning, so the A4 pitch, which normally is 440, but you can select 400 to 480. Then you have bias, which was also there in 81. That adds some preference for the previously selected pitch, which means if someone is holding a note, this allows that note to go off tune more before some other one is selected. And finally, we have micro-tuning. You can import a Scala file to say what the exact pitch of each of the 12 notes in an octave should be. Normally, they are just equally tempered. So here is a real-life example. Again, green above is signal level. Blue lines are the measured pitch. The red ones are the correct pitch. And the y-axis here is MIDI note number. So here we have a singer who really glides up to a note, almost an octave, glides from one note to another, and at the end of a note also glides down, or in between notes, which means that it's nearly impossible to use the auto mode for something like this. Actually, this doesn't sound as bad as it looks. It's, even if the singing is not really to the best standards, it's still acceptable until you start to auto-tuning it. If you quantize this sweep here to notes, then it will sound very, very strange. So this is one case where you would need to use the MIDI input. And the easiest way to do that is just use a MIDI track in order, for example, and use the piano roll or your wheel keyboard to input the correct notes. Then we have the algorithm that computes the corrected pitch, and that is also quite different from the one in 81. In 81, you could select how much of the error was corrected. For example, if the error, if you put that to 15%, then if the note was 2 semitones wrong, you would get 1 semitone of correction. That enabled you to keep some of the natural expression of the singer, so the vibrato, for example, but at the cost of having the wrong pitch. In 82, I changed this, so the static correction is always 100%, always to the correct note which you have input via MIDI, for example, and then you can selectively add the variation. And how is that done? The detected pitch, converted to MIDI note number, goes to a high-pass filter. So that removes the DC component, the static part of it. Only the modulation, the vibrato remains. And then that goes to an envelope generator, and the result of that is added to the pitch, which should be reproduced. So this envelope, actually, it will start fading in the modulation after the quarter second, after the last unvoiced to voiced change. At the moment, these parameters are fixed, but maybe they could be made, I could add controls to change it, but at the moment, I don't think it's necessary. So what you have here is then you get the correct pitch from the start, when the note starts, and then after the quarter of a second, any variations which were in the input will be added to that, which will make it sound much more natural than the perfectly retuned pitch. Then at the end you have the algorithm that will recompute the corrected signal, and that one has two extra controls. You can have a static pitch shift, and you can also have a static formant shift, which is a nice effect by itself. I will demonstrate it at the end. So what is this SOLA thing? It's a well-known algorithm. It's used in granular synthesis. It's pitch synchronous overlap and add. So that means if you know the period of a signal, you take a fragment of the signal of 2 times that period and apply a window. So call that a grain. That's a very small piece of signal which has a very short time, namely two periods. When you add this to the output every period samples, then the result is a perfect reconstruction of the input, of course. But if you change the distance between the grains, you get a different pitch, but with the same formant as the input pitch, as the original. And that is actually the new thing in 82, that's why it can preserve the formants. Because the formants are actually a property of the grain. So what you can do also is resampling the grain, and that will modify the actual formant, and which can be quite a nice effect. So this is a demonstration of that. At top we have the original signal with the windows, and we add all these fragments together, which gives us the same signal again. At the bottom we have the same signal, but repeated with smaller period. But the signal itself is not modified. We just use more copies of it. So now they overlap more, which means not only the pitch changes, the amplitude changes as well, but that is easy to compensate. So this will be a pitch-shifted signal which has the same formant as the same spectrum envelope as the one at the top. And these are actually the spectra of these two waveforms. So in the original we had a peak at 1 kilohertz and at 4 kilohertz, I think. And even if the fundamentals and all the harmonics are different, we still have this peak at 1 and at 4 kilohertz. So the implementation of this is, well, it's not rocket science, but it's not trivial either. You require fractional sample shifts, for example, to do this well. So the current code uses 8-point interpolation, which is much better than quadratic, which uses 4 points. And that is also used for desampling if you use the formant shift feature. So in the implementation, I have a single C++ class called grain, which handles all the gory details of that, the time shifts and the desampling in a single operation. This may be something that is reusable. And then you need some bookkeeping to manage everything, put everything at the right place, and to ensure minimal latency. So, latency issues. For the low voice range, so male singers, we have a latency of around 20 milliseconds. On the high range, that reduces to 15, because the window used to analyze the signal can be shorter in that case. So this is, of course, irrelevant when used on a recorded signal, but some people want to use this live for whatever reason. So for autocorrelation, you need at least 2 periods to have a reliable pitch detection. The window size in the low range is 32 milliseconds, so our estimate is already 16 milliseconds behind real time. And then you have to add all the other overheads. So in the end, we get something very close to 20 milliseconds. The apparent latency depends mostly on the unvoiced parts, because these are mostly transients in a normal singing or speaking voice. So I don't think it's possible to reduce that very much. Maybe you can get 12 milliseconds or something like that, but less than 10, I think it's just impossible. So any claims of modified versions doing that, you should be very wary of them. And, probably just not true, or they are sacrificing some other qualities of the algorithm. Okay, that's it for the theory. If everything goes well, we can do a small demo of this. I have one problem, which is that my laptop cannot connect to the video system here. So to resolve that, we will use high-tech in the form of a smartphone camera and put that on the screen. I'm sorry. So that's how the actual processor looks as a jack application. Yeah, maybe that's better from that side. So at the moment, I have it in an audio session, but it's bypassed at the moment. So I'm using a track provided to me by Will Godfrey. Many thanks. I will first play it without any retuning, so you can have an idea of how it sounds unprocessed. We need the audio. Yep. Okay.
Trailers for sale or rent, rooms to let 50 cents. No phone, no pool, no pets. I ain't got no cigarettes, but 2 hours of pushing broom bars a 12 4-bit room. I'm a man of means by no means, king of the road.
So that's the original.
Trailer.
Oh, sorry. So now, mix. I will enable the plugin. Apps. Yeah. So here you can see the MIDI track which I created to retune this with the correct notes. And I have set the speed. The speed I didn't talk about is the speed at which the pitch can change. It's maximum, and the modulation is minimum. So now we should get a very clear auto-tune effect in addition to having the notes corrected.
Trailers for sale or rent, rooms to let 50 cents. No phone, no pool, no pets. I ain't got no cigarettes, but 2 hours of pushing broom bars a 12 4-bit room. I'm a man of means by no means, king of the road.
Woo! Thank you. So now let's shift the pitch, actually. Let's put it 1 musical fifth lower, which is 7 semitones. Okay.
Traders for sale or rent. Rooms to let 50 cents.
And we can also
No
change the
phone,
format.
no pool, no pets. I ain't got no cigarettes, oh, but 2 hours of pushing broom bars a paper 12 4-bedroom. I'm a man of means by no means, king of the road, trailer.
Oops. Let's tune it up a fifth and also increase the format frequencies.
Traders for sale or rent. Rooms to let 50 cents. No phone, no pool, no pets. I ain't got no cigarettes, oh, but 2 hours of pushing broom bars a paper 12 4-bedroom. I'm a man of means by no means, king of the road.
So that's more or less it, unless you want other versions. I have a version with the modulation enabled. Why not? At normal pitch, yes. And normal format frequency. And I will also limit the slide speed to something more normal.
Trailers for sale or rent. Rooms to let 50 cents. No phone, no pool, no pets. I ain't got no cigarettes, oh, but 2 hours of pushing broom bars a paper 12 4-bedroom. I'm a man of means by no means, king of the road.
So at the moment, this is a jack application, as I said. This will probably turn out to be an LV2 plugin sooner or later. It may take some time because I'm still improving this thing a bit and maybe even add some controls or some other features. So if there are any questions.
Thank you very much, Fons. That was a night. I guess, Will, you never heard your voice so beautifully, huh? Questions, please. Robin?
Would this also work on really short notes? You said the first 250 milliseconds, there's no correction. So if you have like very short
On very short notes, there will be no modulation then. Yeah. Okay. That's maybe something I could make at a control to set that time.
Okay, make it configurable.
I don't know if it's necessary really. A quarter second seems reasonable.
Mm-hmm.
What is important in this regard is what you do in order, because this envelope is triggered by the transition from unvoiced to voiced, or by a gap in the MIDI input. Okay. So for example, here you see these two notes overlap, which means
you don't see it, but yeah.
Oh yeah, you don't see it. So if the notes overlap in the piano track, then the envelope will not be re-triggered. The modulation will continue from the previous note. If the notes don't overlap, then it will re-trigger them.
Let me do some quick exercise.
So a slightly more technical question. Does it run on ARM? And did you use any fancy low-level stuff for FFT computation? So I'm asking if I could use it for live sessions on Raspberry Pi, basically.
It should run on ARM. That is in the 8-point interpolated. On Intel machines, it will use SSE. But the normal single sample code is there as well, so it should work. I don't see any reason why it shouldn't.
Okay. Okay, Jan?
Fons, you were explaining how there is a minimum latency to be able to detect the fundamental shift, and that it's not possible to do it any quicker. I was wondering, because the normal human voice has a very strong octave, like first harmonic. And is there...
Well, not always.
Well, okay, but most do. So is there a trick, like to say you kind of, we ignore that, we try to identify the first harmonic in the autocorrelation and then infer the fundamental and be faster, knowing that it would introduce a slight less of precision, probably.
That's why I wrote an application, this one, to find out if that would be feasible or not, because here you get an overview of what's happened, also as a function of time. And I couldn't find a way to make this reliable. Yeah? If you look at this one, there are maybe 1 or 2 errors. So this is done every 5 milliseconds, the estimation. I think there are 1 or 2 errors on this screen. Using anything more sophisticated, I didn't work. I just get too many cases where it fails. And for a working processor, you cannot tolerate that really. So maybe the answer is yes, but at the moment I wouldn't know how to do it. But okay, it could be an interesting research project, of course.
Okay, any other takers? Yes, we have slightly overrun our 30-minute slot here. Sorry, Roma. Okay, then I guess thanks again, Fons. And I believe after we now heard the music sung by the King of Yoshimi, we will hear from the King of Yoshimi himself at 4 p.m. on the Yoshimi workshop. Anything to add, Roma? Any announcements? Okay. Until then, have a short coffee break with paid coffee. Right.
Well, the paid coffee is better than the free one, so...